In mechanics, you may have come across questions which require you to interpret a given scenario to come up with values for a moving object's displacement or velocity or acceleration, anything like that. For those questions, you may have had a fixed acceleration, and for those you could therefore use these Suvat equations. If you're unfamiliar with those, do be sure to check out the videos on that topic. However, if the object's acceleration is changing, then you cannot use Suvat. It's not a fixed constant. We have to use some other equations. For these, we can have any of one of three types. We can have an equation for displacement, which you may see represented as either x or s. Then you can have an equation for velocity in v, and then that variable acceleration in a. You will know that the equation is for variable acceleration because rather than being a fixed value, an acceleration of 9.8 if it's gravity or something like that, it is given by an equation, which could be just a linear equation or quadratic or cubic. What you may want to do then is get between these different equations. Because we don't have the Suvats, we can't just plug in variables and solve for a consistent thing. We have to each time switch between them, and for that we're going to use differentiation and integration from pure. So if you start with displacement, if you were to differentiate, that would get you an equation of velocity. Take that velocity equation and differentiate it again, that would get you an equation of acceleration. But if instead you started with the acceleration, you could integrate to get back up to velocity, and then if you had velocity, you can integrate back to get displacement. If you're not entirely familiar with how we're differentiating and integrating, of course, as we go through these examples here today, we will kind of recap over that. But if you want a more thorough explanation, do check out those videos. As for just clarifying this terminology, why we're using the word displacement rather than the word distance, displacement is the strict distance between your start and end point, irrespective of the route that you took. So if you were to take some kind of winding path like this, your displacement would, strictly speaking, be just this straight line from start to end as the crow flies. Similarly, if you were to go around in a loop and end up back where you started, your displacement would be zero because there is no difference between your start and your end point. This is just something important to consider in certain scenarios. We will later on be going through such a question where the difference between displacement and distance is important. Before then though, just to clarify with the other bits of terminology, velocity, just as how displacement is distance in a given direction, velocity is speed in a given direction. So how fast are you moving? But specifically, you're going 5 meters per second to the right or straight up or something like that. And then acceleration is how quickly is that velocity changing, so the rate of change, specifically of velocity, not of speed. For all of these then, direction is important, and this just allows us to actually have negative values. You couldn't have a negative distance, but you can have a negative displacement. You couldn't have a negative speed, but you can have a negative velocity. In these cases, the negatives is, well, for the displacement and the velocity, would be telling you you're now traveling in the opposite direction back the way you came. A negative acceleration could mean that, but it doesn't have to mean you're traveling that way yet. If you are traveling forwards and then you're going to slow down and then change direction and come back this way, from here, when you start to slow down, at that point, your acceleration is already a negative because you're now already accelerating in the reverse direction. If you weren't, you couldn't be slowing down. Again, we'll get onto examples of that later on in the actual scenarios. Just for some practice though with our integrating and differentiating, if we were to start with an expression for velocity, so the velocity of a given particle is 9t squared minus 5t plus 7, where t in all of these scenarios is going to be representing time. If we wanted acceleration, Well, to differentiate, we'll do coefficient times power, so 9 times 2 is 18, and then the power drops by 1 just to become 1, so just 18t. And then here, the minus 5t, power of 1, so minus 5 times 1 is just minus 5. The power drops by 1 to become 0. T to the power of 0, or anything to the power of 0, is 1. So minus 5 times 1 is still minus 5. Here, the number on its own, the 7, we can think of as times t to the 0. So coefficient times power, the 7 times 0, that's just going to disappear. So this would be our acceleration here, 18t minus 5. As for our displacement, if I use s here, again, you can have either x or s. When we're integrating, we're going to add 1 to the power and then divide by that new power. So this will become t cubed, and then 9 divided by 3 is just going to be 3. Here, so the t is going to raise to a power of 2, then 5 over 2 here, or 2.5. And here, as already said, we can imagine this is like times t to the power of 0. So add 1 to 0 becomes t to the 1, and 7 divided by 1 is still just 7. Here, though, we're also going to have a plus c, as with any indefinite integration, because we don't know if there was any other term in this higher expression. If we had started with this acceleration, well, the 18t would integrate to 9t squared, and the minus 5 would integrate to minus 5t, we'd have no evidence of what this 7 was. We couldn't say that it was a 7 more likely than any other number. So similarly here, we have no idea if there would be a term here or what that term would be, so instead we'll just represent it as a plus c. In these kind of cases where it's important, the question will then usually give you some kind of context, such as that at time 0 the displacement is 0. So okay, well when you put t as 0, the overall thing has to equal 0, then c must be 0 as well. Or if we'd had it with the velocity expression, when time is 1, velocity is 4. So you put in t is 1 and v is 4, and you'd say, well, what does c have to be to make that balance? Just like how you find out what your plus c is with a straight line equation. Okay. Just the one other thing I want to mention at this stage is just a little bit of phrasing. If we see instantaneously at rest, this is saying that velocity is 0. So obviously at rest means you're not moving, so you have no velocity. But the reason why it may be instantaneously at rest is to say there's this infinitely small moment of time when the thing isn't moving. This occurs at a turning point, such as here on the kind of line I drew before. If on the top here you're traveling in the right direction, and on the bottom you're traveling in the left direction, there must be a singular moment when you are traveling neither right nor left. There is a moment when you are stationary. This is like if you'd done the suvat under gravity. At the top of an arc through the air, at the maximum point, the velocity is 0, because if it was still positive, you'd still be traveling upwards, and if it was a negative, then you'd be falling back down. So just something to look out for. And yes, this notates, therefore, that if it's instantaneously at rest, if velocity is 0, this will be because at that moment in time, the particle is changing direction. It goes back on itself. Okay. Now we have that out of the way, let's move on to an actual question. So as an example, particle P moves along a straight line where its displacement can be represented by x equals 2t cubed minus 18t squared plus 48t. Find the total distance travelled in 5 seconds. This is the question I was talking about before, where the difference between distance and displacement is important. They're specifically asking for distance. So, in the event that this particle turns back on itself, the displacement worked out may actually be less than the real distance. We're going, in case it does something like this, where it turns back. If we're unsure as to whether this will happen or not, to be clear, it would usually happen in like a cubic, we will want to differentiate to get an expression for velocity, and then set that velocity equals 0 to solve for what time that's true for, because if it changes direction, that's when velocity is 0, when it's instantaneously at rest. So, differentiating this, we get that v equals 6t squared minus 36t plus 48 equals 0. Because this equals 0, we can actually cancel through by a common factor, just to make things easier. So divide by 6, you get t squared minus 6t plus 8 equals 0. And this we can break down into two brackets of t minus 2 and t minus 4, because t times t is t squared, t times minus 4 is minus 4t, minus 2 times t is minus 2t, so together that's minus 6t, and then minus 2 times minus 4, because a minus times a minus makes a plus, is plus 8. From here, because these two things are times together to equal 0, at least one of them must be 0 itself, so either t minus 2 equals 0 or t minus 4 equals 0. To make that happen, either t is 2 or t is 4. And if you want to double check that, you can plug this 2 and this 4 back into either of these previous equations, and you should find that it indeed equals 0. So now that we know that it has two turning points before the 5 seconds we're looking at, we know that before it gets to 5 seconds, we're going to do something else. It's going to go forwards, but then it's going to turn around at 2 seconds, then it's going to turn around at 4 seconds again, and then it's going to keep going forward until 5 seconds. So here, also starting off at t is 0, then it turns once at t is 2, turns again at t is 4, and then we're going to end at t is 5. Because of this, we have 3 sections of this journey. We've got between 0 and 2, between 2 and 4, and between 4 and 5. If we were just to do the displacement between 0 and 5, we wouldn't be accounting for this middle bit here, because it would appear as a minus because you're going in the opposite direction, so you'd be taking away from your distance rather than adding on to it. So we're going to want to work out, therefore, what the displacement is at time is 0, at time is 2, at time is 4, and at time is 5. So just simply plugging 0, 2, 4, and 5 into this equation up here for your t. If you do that, you end up with the displacement at time 0 being 0, which makes sense because it hasn't gone anywhere yet. At time is 2, the displacement is 40. At time is 4, it's 32. And at time 5, it's back at 40. These are the displacements. To get the distances, we'll say between 0 and 40, for the first leg, you've obviously travelled 40. Let's just say this is meters, because it's in seconds, and meters per second usually go together. The question would specify if it was important. Here, to go from 40 to 32, the displacement equation will give this to you as a minus 8. But for distance, distance can't be a negative, and we've travelled this extra distance on top of the 40 we've already done, so this is a plus 8 meters, and then again, to go this back, is again another 8 meters. So in total, this journey of going over these 3 legs combined would be 40, add 8, add 8, giving you a total distance in 5 seconds of 56 meters. If we're okay with that, and we can see how we're going to take an equation for any of these 3 variables, and we can either differentiate or integrate to get between them, and how we may just want to think about these scenarios in terms of if we're changing direction at all. Let's see how you get along with a question of your own. Down here, we have that the displacement of a particle P is given by S equals t squared and bracket t plus k, where k is some constant that we don't know yet. Given p is instantaneously at rest when t is 4, find the acceleration of p when t is 10. So, pause the video, have a go for yourself, consider what information you may have to work out before you can get your answer, and then when you're ready to compare, just press play again. So, if we're going to look at when this thing is instantaneously at rest, when v is 0, we'll need to differentiate this. But before we can differentiate, we should probably expand the brackets. So we could say here, first of all, that s is actually equal to t cubed plus kt squared. Now differentiating this, you get your v equals 3t squared plus 2kt. Now we know that the velocity is 0 because it's instantaneously at rest when t is 4, so we can say that 3 lots of 4 squared plus 2 times k times 4. That's going to make it equal 0, but if we want to simplify first, 3 times 4 squared is 48, and then this here is going to be 8k. So yeah, that's going to equal your 0. Now, if we were to rearrange this, obviously you'd minus the 48 onto the other side, so you'd have 8k equals minus 48. Therefore, k would equal minus 6, because minus 48 divided by 8, minus 6. If you want to double check, if you were to do this as 3 times 4 squared plus 2 times minus 6 times 4, yeah, you should get 0 as your answer. We have done this, we've used this first piece of information about it being instantaneously at rest to work out our value of k, and now we know this value of k, we can carry on working out for some other unknowns. The unknown we're specifically after is acceleration, so we're going to have to differentiate this equation again. So if we end up with a equals 3 times 2 is going to be 6, so 6t plus, well, 2k, and the k we know is minus 6. So 2 times minus 6 will be minus 12. We're specifically looking for the acceleration when t is 10, so we now got 6 times 10 minus 12, so 60 minus 12. This is going to give you an acceleration of 48 meters per second squared. If we're good with that, let's just wrap up by looking at one further question from a paper. Now, this question here is displayed slightly differently. We're given that a particle p moves on a straight line, so that at time t seconds, its velocity v meters per second is given by this expression here. So in curly brackets, we've got one row that says v is 7t minus t squared, so long as t is less than or equal to 0, so greater than or equal to 0 and less than or equal to 5. But then v is also equal to 10 minus 2t if t is greater than 5. So depending on the time, the acceleration expression is going to be changing completely. Now, find the acceleration of p when t is 4. Okay, so we're looking for acceleration, so we're going to have to differentiate this v. T is 4 lies within this range here, so we're going to be looking at just the top expression. So if we originally have v is 7t minus t squared, a is going to be 7 minus 2t. We're looking at t is 4, so we've got 7 minus 2 times 4, which will be 7 minus 8. So you have an acceleration of minus 1 meters per second squared. And for b, find the total distance travelled by p in the first 10 seconds. Okay, we should probably just check first of all that this thing doesn't have any turning points. It would do so if either of these expressions could equal 0 in the time the times available. So if we have 7t minus t squared, we can factorize t out as a common factor. So you get t times 7 minus t equals 0 because they're multiplying together. One of them must be 0 in itself. So either t equals 0, or here to make that whole bracket equal 0, t equals 7. Oh, but 7 isn't within this range for this value. By the time you get to t is 7, we've switched equation. So actually, this doesn't apply to us. It doesn't matter. Just to check with the other one as well. So your 10 minus 2t equals 0. Well, then 10 is going to equal 2t. So t equals 5. Oh, but this equation is for when t is greater than 5. T doesn't actually equal 5 itself. So once again, this scenario, it doesn't matter to us. So we don't have to worry about changing direction, not like that previous example. We can just carry on working forwards. So to get to this distance, we're going to need displacement. So we will integrate each of these expressions, starting with the v equals 7t minus t squared. That's going to integrate, if I now just use x for the displacement, to become 7 over 2 t squared minus a third t cubed plus c. Now I have to put the plus c there initially because we have to acknowledge it's an indefinite integral. We don't have specific bounds we're necessarily going between. But because we want to say how far it's travelled from time 0, essentially, we'll be saying that when t is 0, x needs to be 0. So for that to happen, c must be 0 itself. So you can just look at these first couple of terms here. Because we know it doesn't turn around, we can just now plug in that t is 5. So from here you would get 7 over 2, 5 squared minus a third, 5 cubed. And putting that into your calculator, you would get that this particle travels 275 over 6 meters in the first 5 seconds. We're not done yet, but this is the first section. For the second section, we'll again start by integrating. So v equals 10 minus 2t. So therefore your displacement will be 10t minus t squared, because you raise the power by 1 to make 2, and 2 divided by 2 is 1, plus c. Now here, because this is a separate section, we're going to want to consider the displacement as starting again, essentially, to just get what the displacement is in this second section. So what we'll say is that when t equals 5, x equals 0. Yes, this equation doesn't actually happen when t is 5, but if you think of it like when t is 5.00000, however many zeros, 1 after this point, it's now moving off from this new start point. So here we have 0 equals 10 lots of 5 minus 5 squared plus c, so that's 50 minus 25. Therefore, c has to equal minus 25. So now that we have this c value, what this will do is it will just give us a displacement after the 5-second mark. This allows us to therefore just get the displacement when time is 10 without us having to worry about the equation assuming that this is a displacement actually from time 0. So here, if you plug in your 10s, this is going to give you an overall displacement of minus 25. But of course, we're looking for distance, not displacement. So we're basically just going to ignore the minus and say you've travelled 25 meters. It just happened to be in the opposite direction. Therefore, the total distance is going to be the combination of these two answers. So the 275 over 6 plus 25, and that gets you an overall distance of 425 over 6 meters.